people are going to be drifting back from lunch for a little while. So this next panel session, we're going to be focusing on distribution automation, DER integration, and microgrids. So this panel is really going to be focusing on the grid, particularly on the distribution grid. So kind of the flow of the day, like I said, we had identified topics and we created panel sessions around these various topics, and these were key topics that we saw for grid modernization. So this morning you heard about the customer-facing technologies, so that whole Internet of Things, that whole world of technologies on the customer side. We heard about distribution planning, integrated resource planning. That's another key aspect when we come to grid modernization. We're going to be talking about the grid this afternoon. Then we're going to be going into telecommunications, because whenever you're talking about grid modernization, any aspect of grid modernization, you're going to be talking about communications technologies, communications networks. So we've got a really good panel session that's right after this one on communications technology. And then we're going to wrap up. We're going to be talking about architectures. And we're not talking about building houses. We're talking about grid architectures. We're going to be talking about, who needs to be communicating with who. And when we start thinking about, particularly we start looking at third-party aggregators and new players that are going to be operating and providing electricity services, talking about architectures and what organizations need to be connecting with what other organizations becomes really critical. And so we've got a good panel at the end of the day talking about grid architectures. But this panel session, and I want to introduce our panelists and introduce this particular session. Colton made the comment earlier today, right, the grid that we have today is not going to be the grid that's going to support us as we go into the future. And so what we really want to talk about on this panel session is, well, what is that grid of the future? What are the capabilities of this grid of the future? And in particular, to hit that 2045 goal of having 100% renewables, what are some of the challenges that are going to be on the grid? And then what are some of the solutions that are needed to overcome those challenges? We have 5 panelists, again, 5 really leading experts within the industry. I'm going to introduce them kind of in groups, because on the panel we have representatives from GE, Siemens, and S&C Electric. These are 3 of the largest equipment manufacturers that serve the electric utility industry. So if you're driving, if you're looking at some of Hawaiian Electric substations or the equipment that are on poles, very likely that the equipment you're looking at is coming from one of these 3 manufacturers. The traditional equipment that's been, the utilities have been relying on for 100 years, transformers, switches, these companies make those. But more and more, they're building these new, they're providing the new technologies, things for distribution automation, for microgrids, for DER controllers. So these large vendors are providing those types of solutions. So let me introduce 3 of the panelists. Mike Edmonds is president for USA Business for S&C Electric Company. Mike Carlson is president of Siemens Digital Grid North America. He's also the CEO of eMeter. And Elliot Elliot, I'm butchering your name. Thank you. Is the microgrid sales leader for GE Solutions. I'm sorry about that, Elliot. We also have 2 other companies. We have Connect DER, is a provider of grid integration technology for solar and other distributed energy resources. And Whit Fulton is the CEO of the company. And we have STEM, is a company that sells energy storage systems for customers and provides a data analytics platform that provides customers with insight into their energy usage and cost. Tad Gauthier is Vice President of Hawaii Operations for the company. So these are our panelists. Similar format that we had earlier today. I'm asking each of the panelists to talk for between 8 and 10 minutes, and then we're going to open up for questions and answers. So again, please ask questions. Somebody had asked a question about microgrids this morning. This is the group to ask the questions on microgrids. They'll be able to provide you the answers. So with that, up first, Mike Edmonds.
Well, good afternoon. I've got the shift after lunch, so I'll do my best to keep you all thoroughly engaged. And I've planned it to be about 10 minutes. So first, who is S&C Electric? Some of you may ask. We, despite my accent, are based in Chicago, Illinois. We've got about 3,000 employees, and we really specialize in electrical power. In fact, one of the things I would be clear about our company, been around for over 100 years, is we don't copy things, we actually truly innovate. So each one of our devices, whether it be a switching device or some new energy storage device, they all have to have a unique problem they're solving. Otherwise, we won't actually create and do it. And part of that is, and this is the one picture of a building which you'll find in my presentation, that is actually the Advanced Technology Center in Chicago, which is actually the highest fault level rating power testing capability in North America. Basically, we can blow stuff up. So, which is really good for speeding up the development cycle of a particular item, but is also really good to actually test configurations for customers. So there's a particular customer problem and you want to try it at full rated use in the grid, we can actually do that in this laboratory. So that's the reason for that. Most of our business is actually, frankly, in North America at about 85%. So anywhere where there's a US-style grid, which what that translates to means an unbalanced grid, for want of a better word. So you have single phases, you'll have different ways of running the grid. That's what we really specialize in. So you won't find us in sort of deep parts of Europe. You'll find us in some parts of Europe, for example, but a lot of places like Brazil, Australia, New Zealand, those sort of places, as well as around here. So next slide, please. So no, it's not broken. Just wanted to get all your attention away from looking at a picture. The other things that we actually work on are things around like energy storage, microgrids, switching and protection. And with that end today, I wanted to actually share with you 3 key insights, looking at the 3 segments for our panel to talk about. One is around distribution automation, where I'd like to show you that distribution automation also improves grid resilience. The second insight I'd like to share with you is as you add DER to that distribution automation, you start to make a platform that enables more renewables into the grid. And both of them combined create a really flexible grid. And one of the things as you add those together is the third stage is microgrids, because you can have a deliberate microgrid, but you could also have a unplanned microgrid by actually having the capability of storage as well as DA as well. So I'll talk a little about microgrids as well. So next slide, please. Here, I just wanted to recap, and there's an interesting conclusion at the end of this. You've heard this morning about the grid moving energy really from top down, generation, transmission, distribution. And in fact, the regulatory models for that were actually in Ronald Reagan, Margaret Thatcher days, that long ago, where we looked at moving wires apart from generation, apart from transmission. And that's actually creating some barriers today in some of the new innovations that the grid could actually accommodate. But as the grids move forward, we've really called it here the integrated grid, the ability to add new and different features to it. And essentially, I like to think of the energy now moving sideways to neighbors, as well as backwards. You heard that this morning. You can get some pretty impressive power back into the grid, as well as the traditional power from the center. That actually creates a really interesting dynamic, and not a good one. There's a couple of things that this creates, and that's the opportunity for what I'd like to call blinks, the ability to have very short durations and no power. That's bad for PV. because the smart inverters will, with a momentary outage it's called, will lock out for 5 minutes. And we'll actually go through that the consumers today are actually seeing blinks as being the major sort of irritant of the grid. And quite often we're not even measuring it. So as we go through this integrated grid, we're starting to see a change in expectations for performance. And that also goes to how do we measure the grid. So one of the things we measure of the grid is something called SAIDI, a very electrical engineering term, invented way before, I think the 60s and onwards, but we still measure the grid in that very old analog clock way of thinking of the grid. Whereas today, the lack of power for 5 minutes is significant. And the lack of power for less than 30 seconds is significant. I'll show you some examples as we go through that. So next slide, please. So with this, I don't know about you, but when I'm traveling, I use an app on my phone called Waze. I presume some of you are familiar with Waze. So we actually have a pretty smart phone in our hands, a computer. It talks to other users nearby, reroutes us when we get in a wrong traffic situation. In the case of me, and yes, I have learned to drive on this side of the road 20 years ago. The case of me, I can actually get myself anywhere quickly as I can. That's really called distributed intelligence. That's not going back to a mothership. It's not going back to a centralized mainframe to ask permission to ask what the next action is. That's actually sharing information. So think of that as distributed intelligence. That is something that we, as our foundation for distribution automation, having devices to be able to talk to each other. That's key in scalability, because if you have two devices, two of them can talk to each other, and you can add them, and so it becomes scalable. That's really important for a DA, distribution automation approach. You don't have to go big bang. You can actually go at a much more scalable approach. And that has some interesting abilities to be able to do that. Some of the capabilities you don't need to have communications. You can actually, sensing the grid itself can make changes. And as you add communications capability, you can get actually much more from the grid. So next slide, please. So this is a real example with some results from here as well. So this started off in I want to say the end of 2011, really to get scale. EPB Chattanooga really started to change their grid from a very traditional manual switching grid to a grid full of smart switches that talk to each other. They were also privileged to have fiber optic communications, so that had a particularly good advantage for things that they could do with that. They installed about 1,200 switches over time, and the graph actually shows the penetration. As you install more and more of these switches, the more of the performance of the grid improves. So you actually start to save customer minutes lost. And the picture there is looking at a real event, 2013, where a tree fell across a right-of-way and actually knocked out power to 12,000 homes. So the system at the time, well, the way it reacted was to, again, a Waze approach, talking to each other. Within 42 seconds, 98% of those people were re-energized because it had distribution intelligence in there. And then the following 2% were re-energized about 3 minutes later once control got involved. But that starts to show you some of the power about how you address it from here. So next slide, please. There's been, again, look at the changes in automation and the changes in outages. And there's been some really great successes. So I'd like to set up the next one, which is, if you could just do the next slide, please, ComEd. Wait for the back slide to go. It's revealing itself slowly. No surprise. So ComEd filed a rate case that had to go through legislation in the state of Illinois to actually improve reliability while reducing customer bills. And actually have got some great improvements, and they've had some real game-changing improvements in the sustained outages, for want of a better word. But if you go on to the next slide, please. Here lies a challenge, and I mentioned those momentary outages. This is a hospital. This is the whole hospital range in the same sort of territory where momentary outages. Now imagine that, a hospital, momentary outages. You have equipment that people's lives depend on. And 30 seconds without an equipment could be pretty serious. So this is actually an event this year where there were two presenters, one saying, look how much I've improved the reliability, where the next speaker got up and went, wait, what? No, it's got worse for me. I don't understand what you mean. And it struck me that we're measuring different things. So one was feeling momentary outages, the so-called sustained here, which will impact renewables. And that's a key thing I want you to remember from here. As you want to put more renewables on the grid, keeping the grid available to keep them on is going to be an essential part of it. And if you have these momentaries or blinks, you're going to have systems going off for 5 minutes and all coming back on at once. So you're going to get this big seesaw effect. That's why it's particularly important. So next slide, please. So that's really the reliability side. So distribution automation, and the example there I showed was resilience of the grid improving. Next slide, please. I just got one slide on each of these. This is to look at energy storage. What I would say with storage is such a changing market. We've been actually providing storage systems ourselves. We would call them integrated. Because we've got the inverter, the chemistry, how you control the chemistry, how you fit it in the grid, and how you survive it. But in that 10 years, do you know we've had 6 chemistry providers go disappear, go bust, not even Chapter 11, they vaporized. I've actually got $2 million worth of lithium ion, if anyone wants some. And you don't, because it turns out lithium ion are all different. So you can't get one manufacturer of lithium ion and think of something different from here. So it's a real changing system. Here we've actually got locations here of a NAS battery, because 10 years ago cattle deferment was a big issue. And then we have a community level, so that's really at the house level to supply. The conclusion I've taken from energy storage is that it's still going to evolve. Where it goes on the grid still needs to be defined, because grid benefits are all going to be different. But it's all going to need to be connected to a more automated grid. So next slide, please. That leads me into the final part, which is really, once you've got storage, once you've got other devices, you can have unintended microgrids. So microgrids, what do they mean? So put the next slide up, please. First off, microgrids aren't new. If you've been on a ship, it's called a microgrid. It doesn't have a big cable back home. So it's existed for a long time. What's interesting today is microgrids and how they actually operate, whether they connect to the grid or from the grid. So these are actually 3 microgrids I deliberately picked, which are actually ours based here in Hawaii. And there's about 3 more we're working on that will be announced this year. Next week there'll be a utility microgrid announcement over a microgrid built that can actually take itself off the grid, so-called blinklessly, if you wouldn't know it's come off the grid, operate on its own with renewables and diesels and others in that particular case, and reconnect to the grid. Now that sounds pretty simple, but behind that lies a lot of engineering. I heard you say this morning, someone say about fault levels falling. That's a really big issue, because each time that changes, how do you make sure the system is safe, 1, and 2, if there's a problem, how does it isolate correctly? And you've got to think that when the microgrid's connected to and not to the grid, and then actually how you develop it from here. But it's certainly, I would observe in the last 3 years, the activity and certainly our business in microgrids has increased. So there's clearly is ability. The challenge, this morning's question was, is regulation. Did you know in Texas it's actually illegal for the company there, the T&D company, to own storage? Legislation's passed a law to say no storage. So legislation has to be changed. You have other utilities on the mainland who aren't able to develop microgrids because the PUC has deemed that that would have a privilege level of service to a certain number of customers because they have a higher reliability. And there are others who say that you can't own generation. That needs to be owned by a separate company according to our regulation. So I would say that it's not a technology barrier, it's actually a regulatory barrier. And it's going to be a while as all the states to line up. But that for me has been the big regulatory barrier for us to move forward with microgrids. And that leads me to my last slide, which is the end. Thank you.
Well, good afternoon as well. We on the panel had a debate who's going to start because we feel the consistency of what you're going to hear from us, it might get a little bit repetitive. So Mike won the honors. But if I look back, it's encouraging to me. I started in this industry when smart grid, utility of the future, long time ago, and to some extent it's still being defined. You know, what is a smart grid? And we'll get to it in a minute, but I would suggest we probably have the same thing going on with what is a microgrid. But as far as what does distributed energy look like and how are we going to move forward, I think we understand it. The question is, and I agree with Mike's last comment, it's not so much a technology challenge, but where does it sit in a regulatory and business operating standard? So next slide, if you will, or first slide. We look at this from a Siemens perspective and again, Siemens, if you look at our legacy, we started as an electrification company in the late 1800s. We, in the recent 25, 30 years, have moved to an automation company, but now where we see, and especially related to the grid, is a digitalization company. And how are the equipment and devices that exist and operate the grid in a relatively high degree of confidence, reliability, and efficiency, how do those move forward to the next level of opportunity? The thing we've injected into this model that didn't used to exist is variability. I started in this industry as a finance guy. I got into the IT side, and we had a party one day that discussed updating the model. I said, you know, we had a cake. There was a lot of people that had dark rings under their eyes. I said, what's the party for? You know, the finance guy doesn't know anything. We updated the model. What's the model? Well, the model on how the grid is planned and operated. Okay, any big changes? No, we're 3 decimals to the right. I think we moved a couple of units. It was predictive. It was understandable. It didn't have the variability that we're now starting to see, good or bad. And we take the position it's good if we can start to understand that variability and leverage it for optimization into the grid. And that's going to require a digitalization model that brings the equipment with the data and puts it together into the optimization of operating decision. It's really boils down to 3 dimensions. You've got the equipment, which is going to iteratively improve over time, but it exists today. You need a communication channel to move and connect that equipment into any number of, you can talk IoT, you can talk analytics, you can talk control centers, but that information needs to move, and then we need to provide analytics. And as smart and knowledgeable and capable as our grid is today, the expertise needed to manage the multiple variables in the real-time sense of optimization tomorrow isn't going to allow the model. It's not going to allow the human. It's going to have to leverage the data, the analytics, and then the presentment of that in multiple areas. So if you go to the next slide. The other thing is we look at this from a DER overview, that perspective of bringing the environment together, driving it into not only the grid operation, but the integrators, and the debate is ongoing. It's going to be interesting to see where are the drivers. Will it continue to be the utility? Will it be the independent owner-operator? Will it be the disruptor? Actually, we see the independent asset owner-operator, the utility continuing to be the core drivers. The disruptors, the question is, will they disrupt and leave it to the rest of us to figure it out, or will they disrupt and bring a new business model into play? And again, back to my colleague's reference, that business model and the regulatory structure around it is probably the biggest barrier that we need to see addressed going forward. So as we focus on these areas of planning, design, network planning, operations, and then finally the business model that will incent it, those are all combinations that need to be in place, and there's a variety of participants in the model being worked on today. Next slide. So specifically, as we've looked at this, and you look at a distributed energy management environment, it really requires three components. Definitely a planning, then an operations, and then ultimately a settlement proposal. I think what we're seeing right now is the debate over and the question of, can the system handle more entrants onto it? It can right now, but the bigger question is, can it handle it optimally? And who's going to be the balancing entity to ensure that all of this great new capability doesn't in fact erode our grid reliability, but enhances it and then moves it to a better and more efficient operation? So these three components are definitely a piece that we would argue does not exist today. The independent owner-operator, not a big planner in conjunction with most of the utilities. We're seeing here, a few other places around the country that are taking a more active engagement in what that planning looks like, but there's still the challenge of history and reputation of the big bad monopolistic utility. How are they ever going to enable something that doesn't allow them to succeed? Those are things that need to be put together in a much more integrated and detailed level. And that planning and fidelity that we've applied to the transmission generation side, that now needs to move down to an integrated distribution side. So next slide. Must be that mid-presentation pause to catch up, Mike. So we've looked at this, and again, the operation, we still look at the grid stability being the purview of a, if you will, a DSO. And where is the DSO going to be designated from, pulled from? Arguably the utilities, whether it's in the United States, in Europe, in Asia, we've seen the utilities be the best and most proficient at operating the grid. The question is, how do they allow the new participant entrants and integrate what they're bringing to the table into the rest of the technology? Certainly the ADMS, SCADA operations, outage management, but ultimately market and participant from an economic perspective have to go along with it. As we put this together, we've seen multiple examples of different models. Some, the utilities are embracing it as an option and a solution to get to 100% renewable standard. Others are looking at it as they'll figure it out. New York is probably one of the more proficient right now in driving a market participation. And back to the microgrid, we're actively working with about 250,000 customers in Brooklyn to establish a microgrid. The focus there is not sustainability, it's not reliability, but it's economic opportunity and choice. And so now we're seeing market engagement into microgrid at the residential participation level. Had an interesting discussion with a HECO colleague that said, hey, do we really think customers are going to actively manage and trade energy on the whatever market exists? Probably not. But can you see an aggregator pulling it together? Can you see automated transaction settlement occurring? We're using blockchain technology for some of this, which are micro units of settlement, whether it's pennies, certainly it's not dollars and cents. So as we put this together, this integrated distributed energy management is the technology that needs to be facilitated through planning, connectivity, and analytics going forward. So next slide. As we put this together with microgrid, and we tend to look at microgrid, well, as Mike referenced, it's a very market-sensitive term right now. It's hot. It's got the brand around it. But that's about what we see it as. Distributed energy is really microgrid, just one component of that. Microgrid, demand response, distributed energy generation, distributed energy distribution. All those coming together, but certainly needing to see all the different aspects as we put monitoring, balancing of power, scheduling, transition. And again, every one of the participants in a distributed energy model seem to have their own unique driver. But they ultimately settle around a reliability strategy, a sustainability strategy, or what's growing in interest, whether it'll be fulfilled as reality, is an economic strategy. So I believe last slide. So as we look at this, the two key developments from a technology perspective are really probably that combination of IoT, probably one of the better next generation plans. Right now we look at the IoT from an industrial perspective of about 15 billion devices connected globally in an IoT model. A large percentage of those are meters. Meters represent, close to 10% of that, and maybe one of the largest single category components. But looking at what that's going to do over the next 15 years, growing to 50 billion devices. The power of that interconnectivity of devices, edge computing, enterprise computing, and the optimization for business rules is what we see as the future of distributed energy. It's also going to be the gating control over how effective we are in deploying it, how pervasive it can become. So as we put this together, our focus is probably, while we have good partners, we're seeing good participation, our peers in the industry from a technology deployment. The real challenge, again, is back to the regulatory and business models that present themselves as barriers. And how do we turn those barriers into opportunities? How do we let the disruptors keep pushing us, which is definitely an advantage, but not letting the experts in the industry be held back from the barriers that are disruptive from a business perspective. So thank you very much. Look forward to the questions a little bit later.
Aloha and mahalo for having us here today. This is a very exciting opportunity for us to be able to share some thoughts and also learn as well. General Electric has a very long relationship with Hawaii. It first began in 1881 when King Kalakaua visited our founding father, Thomas Edison, in New York City. And King Kalakaua was very much interested in technology. And when he visited Thomas Edison, there's a very interesting article about that visit back then. Met him on Fifth Ave and all that, and he ran ideas to Thomas Edison about energy. He goes, what if we can put a steam boiler in a volcano and make electricity from it and things like that? So the challenges for Hawaii fascinated Thomas Edison. He sent one of his engineers, a gentleman by the name of David Smith, over to Hawaii, and the result of that 5 years later was the first microgrid at the palace. There was a steam generator there, and then not too long, 2 years later, they established a hydro generating facility to provide lighting in downtown Honolulu, which then began the HECO. So this relationship's continued throughout those years. As more recently, over the past 10 years, GE has been working with HECO, HELCO, NECO, and also KIUC in developing models to study the amount of penetration of renewables that can occur to achieve the goals of the RPS. And so it's with great pleasure that we continue this relationship, and we're very honored by it. So what I'm going to do is very briefly give you an overview of what lessons learned from DER and microgrids and share some insights. Next slide, please. So our view of microgrids is nothing unique in terms of the different functional blocks. We're not purists, as Mike noted that it can be different things in terms of distributed energy resources, but in terms of the distribution system, there's different layers out there. It's not just one microgrid or a community at the distribution or feeder level. It could be virtual power plants. You heard a lot about that earlier today. And then, of course, GE is very much involved at all levels of the technologies required, from generation batteries to microgrid control and distribution automation. So the key message we would like to give here is don't be too purist about how you're looking at microgrids. Some people say it has to island and things like that. That's probably true, but But look at the different functional building blocks within a distribution system as potential microgrids or nanogrids in the future, and how they interact on different layers. Next slide, please. I think the three key principles when you look at the challenges from generation to the grid to the end user are three things: visibility, control, and optimization. And usually that's a journey. All right. First, you want to get visibility. I think, particularly in Oahu, there's been great steps towards that direction. And then, of course, visibility is great, but that's information. But the question is what you do with it, and that's where control comes in. And once control is in place, how do you leverage the information, the ability to control the different elements within the grid, and then begin to optimize the system? And it's a continual, iterative process. I heard a comment earlier today, like, oh, let's start from zero and rebuild the grid to the RPS, and that's not going to happen, right? So it's important to keep these three principles in mind as you iteratively get there over time, okay? And even within each of these functional elements, from generation, grid, and the end users, there's various types of capabilities that they should have. The information and analytics that comes from the visibility and the ability to control these different elements are essential in coming up with innovative ways to optimize the system and get towards the stated objective of the RPS. Next slide, please. All right, and here's another view of how we look at the system components of a microgrid. Remember, these are all very hierarchical, and they're not firm boundary conditions between them. But you have substation automation, you have the DER integration and optimization of that, and then as you get closer to the head end, the ability to do operational planning or real-time operation commitments, more at the utility level, managing these disparate assets, if you will. And then at the management level, there's different types of ways to manage microgrids, from automation, optimization, market functions, and things of that nature. So we kind of view microgrids as very hierarchical. You can start with a home level, or nanoscale, and then go up to the feeder, distribution level, virtual power plants, et cetera. Next slide, please. So I'm going to give a quick example of how one project we did with SoCal Edison in terms of how we develop an approach, a very low-cost approach to get visibility, control, and optimization. And in this project, what we did was we developed an architecture where we could take a very low-cost GE radio and slap it onto various DERs. In this case, there was batteries, there was some PVs, and other assets that, since they're like edge devices, had very limited communications ability in terms of being able to communicate on a field message bus, okay? And what these radios did was convert the basic, Modbus type protocols into more functional and capable communication protocols to have the speed and ability to do peer-to-peer communications with various different assets out there, as well as the head end of the utility. So by being able to take these edge devices, which had very limited, or edge DERs, which had very limited communications ability, we're able to then provide fast communication protocols like IEC 16850, and then have communications and control at that blue layer over there, so they can communicate amongst themselves, but then also go up to the utility scale to provide the ability to do fast controls as well. And in this application, we did volt bar control with these various assets. But the architecture we developed here is so inexpensive, you could bring this design down even to the home level. These radios are very expensive and have the ability to be installed very quickly and cheaply. So this is one good example of a pilot project we did with SCE that reflects the philosophy of getting visibility, control, and optimization out there in a very low-cost way. Next slide, please. Another aspect of developing DER systems and microgrids is community-level engagement. So when I talk about community in Hawaii, I don't only think of geographical location, but also think of the Department of Defense and the military bases. And one of the key challenges is you can have a large integrated resource plan, but then each community has its own needs, particularly the DoD, and each base has their own respective needs. It's very essential to have to engage the stakeholders at that level to help them understand the value proposition, but more importantly, develop a model, if you will, that not only addresses their opportunities, develop a business case, but also interact with utilities and meet the needs of utility as well. Next slide, please. So you heard from probably, I counted 7 or 8 people today make mention of what's happening in New York State. So I'll give a very high-level overview of what's happening with what's called the Reforming Energy Vision. This is probably one of the more advanced, regional activities at the PUC level to address, I would say, mostly resiliency, reliability, but also renewables integration. And what New York State is doing here, particularly in this example, what's called New York Prize. Mike mentioned he's got a couple of customers that he's working with, as well as we do. The PUC is looking to engage industry, communities to develop a unique design to meet the objectives of renewables or resiliency, but do it in a way that is very much amenable to innovative business models where you can have aggregators or third-party owner-operators or even energy services companies that interface between the community and the utility to pull together various stakeholders. One of the biggest challenges, particularly when we have multi-facility microgrids, is you have different stakeholders, how you pull them all together, whether it's generating assets or other DER assets, and then into a single contractual vehicle that they can work with the utility, okay? So what New York State did is have a 3-stage process. One, a very high-level evaluation for each city that's involved to determine if there's something there, right? And then that's stage 1. And then stage 2, which is what we're currently involved with right now, is an effort to develop a plan and a design that is bankable in terms of financing, okay? I absolutely agree with Mike's comment about the regulatory environment and the innovative business models that needs to change in order to enable these types of things. So this is a good example. Not everything they do will fit in Hawaii, but in terms of developing an approach that engages the local communities, but also has a financiability element to it is essential. Next slide, please. All right, some parting thoughts. So we have this 100% goal here, but it has to be an incremental journey. We can't design the system for 100% today. I think there's some very key principles that should be involved, namely, whatever your generation mix is, there should be a set of generation assets that have certain characteristics as a baseline or a foundation. And these characteristics should be things like ramp rate control, AGC, dispatchability. Doesn't matter what assets those are. I'm not advocating any specific generation or DER asset, but if we have a foundational baseline of those types of assets that have those types of characteristics, then you can build your microgrids and your more PV on top of it, and et cetera. So don't try to achieve it all at once, but just make sure you follow the earlier principles of visibility, control, optimization, but also have a set of baseline assets that have certain characteristics that can ensure the stability of the grid. You got my second point. Once you have visibility, you focus on control. I think the third point, align the community needs with the utility is key, particularly with the military bases here. There's been a lot of planning and interaction with ECO and the DoD for respective bases, but I would encourage any DoD stakeholders, if there aren't any here, to look at master planning, not just for their individual bases on island, but collectively understanding what their goals are on island with all the bases so that they can align them much better with the goals of HECO. And then I guess this is an echo of Mike's comment, but the regulatory environment and framework that is conducted to grid services or innovative business models is essential. There's a lot of lessons learned still to be had in that area, but the more you allow third-party innovators to develop solutions and business models that that can solve these problems, the quicker we all are going to achieve our goals. So I want to thank you all for this opportunity. Have a good afternoon.
I lost my voice. I will try to do my best to be quick, so we'll get through this together. Yep. Hey, my name is Whit. I work for a company called Connector. I'll see if I can get through this here. My deck will be completely different from what you guys heard so far, so at least there's that. You'll find out what Connector does in just a minute. Next slide, please. All right, very simply, the grid is the greatest asset the utility has. Very simply, the power generation itself is highly commoditized. It's come down cost. Gas is the margin in most places. The one thing that the grid, that the utility has to offer that's special, different, and really powerful is the grid. But it has to transform from what it is today to something that's a little more rich and deeper. So next slide, please. Ultimately, the grid is the basis of a market, a transactive market. So, and just like NASDAQ or most of the major stock indexes, what you have here is a grid that is strengthened by the number of participants and market participants within that grid. The more market participants you have, the better and higher value that grid is. So all policy decisions around moving the grid into the future need to be geared toward ensuring strong market participation from all market participants. Next slide. This is a great diagram that was put together by our friends at SEPA. Thanks, SEPA. At the end of the day, the DRs are this hugely, vastly underutilized resource on the grid. They can provide so much more than they are right now. Effectively, you have a series of grid supporting resources beyond energy, ancillary services, voltage support, et cetera, et cetera. Right now, in our current, the way that we compensate DRs doesn't take advantage of any of that. In fact, next slide, please. Net energy metering historically is basically, buy all, sell all, give us your kilowatt hours, we'll give you money. That's created a perverse incentive to put DRs wherever you can for the same compensation, and ultimately leading to imbalances in how the incentives between what the grid needs to be robust and supported, and really what the market can provide. However, I think I'll be one of the few guys who's going to speak to you today who's going to come at you from the solar industry perspective a little bit, in large part because what we do at Connector is build a bridge between the solar industry and the utility base. Next slide, please. All right. Customer self-supply. This is not the customer, but this is effectively the solar industry in Hawaii right now, at least the residential level, and reacting effectively out in the wilderness, getting really strong, getting really strong, getting really good in installing systems with storage and solar that effectively pull people off the grid. That is what the current tariffs that are out there that are still remaining are incenting people to do. And customer self-supply, when it came out, had a very good reason. It was a stopgap measure to really, stabilize what was available for people to, for the grid within Hawaii. But the problem with customer self-supply is it's creating an incentive for people to get off the grid and not to create the bridge between these DER resources and what the grid needs. So next slide, please. All right, so we already mentioned a little bit, we talked about the new capabilities that DERs can provide, given the new YOLO standards that are being promulgated right now. These inverters are going to hit the market very soon. The low-hanging fruit from those inverters, you don't need storage for them, is really these two sections I've circled right here as like the sweet spot. There are ways to take advantage of those capabilities so long as the market structure around them, the tariffs around them, are adequately compensating the owners of those DERs for those capabilities. Once you layer in battery storage, you get a much richer set of capabilities available to the grid. But starting out, you don't need to do that. Battery storage is great. The cost economics at large scale aren't quite there yet. So the low-hanging fruit for the near future, next year or so, is probably the inverters themselves. Next slide, please. So now we're really down to the question is, if you have a strong market operator that incents DERs to be in the right places in the right way and compensating them and bringing them into the market in a way where utilities say, great, this is what I need from you, how do you get to them? There's still that last mile argument. And people have talked about, there's two primary ways of doing this. One is via an aggregator. We talked about that a little before. Real world implementation of aggregators for the residential level are some of the big providers like Sunrun, Solar City, in Hawaii, Revolution. They have the strength, the wherewithal, and the back-end technical ability to be that aggregator model between the DER owner and the ultimate market. They can abstract away the complexity that we talked about, where there's a lot of variability in the way the DER signal might work, and provide a simple compensation model for the customers. But the question is, what happens to all the other customers out there who are being sold onesie-twosie models from the rest of the solar industry? How do they participate in that market effectively? And the argument that I make here is effectively that you need a direct signal market operator that can handle those remaining people. It could be the utility. The utility could become a virtual aggregator for those remaining people out there. But ultimately, you have to have a market model that doesn't leave anyone in the dark. Everyone has to have the right to participate on an equal basis. Next slide. Very briefly, this is what Connector does. We make a meter collar that sits between an electric power meter and meter can that creates a plug-and-play interface for solar PV. We work with a number of utilities on this because it does touch the meter. It's really necessarily a part of utility infrastructure. But what we do is really twofold. On the one hand, what we do is we provide a standardized way to connect the solar PV to the grid. It's got a circuit breaker in it. We're able to avoid a lot of the difficulties in wiring, especially in the East Coast, but even in the West Coast and Hawaii, we're able to avoid having to do service panel changeouts or work with the difficult wiring situations. You standardize the process. You made it very simple to connect. Now that said, that's only half of the story. So interconnection is great, but if everyone could just interconnect very easily, you'd end up with the same issues we talked about earlier. So we layer on top of our basic model revenue grade metering for the PV, for the whole house, relay controls on the PV, so for sort of blunt force curtailment on a very limited basis, and then ultimately an Ethernet bridge between the connector product itself down to the inverter. Ultimately, what we would like to do is, in addition to lowering the cost of interconnecting, integrating solar, in the longer term, we want to create a simple plug-and-play conduit between those inverters and a back-end system of addressable assets that the utility system can tie into and begin to create compensation models for those inverters automatically. Next slide. Make sure I get water in. All right. Very simply, one of the things we're asked to do is talk about what we're doing today versus what we're doing tomorrow. Today, I talked a little bit about the fact that the product we have, you can see it a little more clearly here. We have a DR power interface. We've got a data interface, and we're taking away all the complexity of connecting those devices to the backend system, to the grid. But we can go much farther than that in the future. Where we'd like to go is effectively create a socket you plug into that's on every meter and throughout a service territory. And the second that DER is plugged into that socket, the connector figures out what it is, queries it, and registers the asset in the cloud for automated interaction. So effectively, between the communications networks out there and all the other things, and a lot of the new technologies out there, a lot of the technology issues fundamentally have been solved in order to get to sort of the modern grid state. The bigger challenges are what the compensation models look like. Next slide, please. So this is my lots of words slide. I apologize for it. At the end of the day, I boil this down to three major missing links to get from where we are now to where we need to be as far as being able to bring the DERs into the grid very easily. The first is, how are these assets talked to? There is secure Ethernet. That's one way. There's utility MI. There's cellular networks. But ultimately, you need to have a secure communication network. Security is paramount. important, but in a lot of the projects we're working with our utilities, we're finding that a very substantial chunk of the value out of DERs is, at a real-time basis, is enabled by day-ahead scheduling with operational controls. So you don't necessarily need high-speed addressability of all your endpoints on the grid. Secondly, interoperability standards. We've talked about this previously. I won't go into it now. Third, participation requires a robust market model that can bring customers in with a certain level of certainty as to what they're doing. Next slide, please. This is my second to last slide. I'll be very quick. But ultimately, there's a lot of different ways you can build a market. And if you want to build a market that works for everybody, there are three primary principles, as far as I'm concerned, that really need to have primacy over the other principles. The first is fairness. No thumb in the scale, no inadvertently benefiting any specific group of participants. Second is transparency. It has to be auditable. So if you're moving to a market where you have these DERs being able to provide these additional services, what the cost is or the benefit is of that service in different places needs to be auditable so someone can go back and check it out and say, okay, this is what happened, this is why we're compensated this way. And the third, mitigating against all that transparency and the fairness principle, is the certainty. You can abstract away a lot of those ups and downs that are confusing for various customers into a very simplified market model saying, okay, I'll give you, $5 a month for the ability to turn down your inverter occasionally within these bounded constructs. Very similar to how they use traditional low control programs for houses. There are about 10 different market models that I'd be happy to share with people once I have my voice back. I won't go into now, but ultimately, at the end of the day, last slide. To summarize what I'm saying here is really, you need new markets in order to serve the needs that are out there. You benefit by paying your customers for participating in those grids, and you make better customers out of market participants. You use all the capabilities that are available from the DERs. You don't leave any sort of value hanging on tree or on table. You keep the money in Hawaii with your customers. This is sort of obviously more aimed at the Hawaiian market, but ultimately there's the benefit of you paying your customers as market participants and keeping them happy because they're contributing and participating. And this is the way we get to 100% renewables. Thank you.
Okay, hi, my name is Tad Glothier from STEM. I think I'm the last presenter, so we'll have hopefully a few minutes for conversation after this. I think in our description, it maybe came off our website, the words energy storage weren't used, but I would call us a distributed storage company. I think for marketing purposes, we probably call ourselves more of a software and platform company like some of the other folks this morning. It's an important distinction because we don't make batteries. The batteries that we use in our energy storage devices come from large global scale companies, and what we do is we aggregate those batteries. We try to use them for two things at the same time. We try to create a customer value in terms of savings on a bill, and we try to create a grid value in terms of aggregating them, letting the utility or the grid use them for some purpose. So next slide, please. That's what I just talked about. Next one. What we did in 2014 was launch a pilot here with Hawaiian Electric companies to deploy 1 megawatt of storage. And so we went out and enrolled customers. They're in a kind of co-branded experience. So you see the login page that they get here with the Hawaiian Electric company's logos and the STEM web page. And we offered them to participate in an energy storage pilot where they would save more than they pay. So they pay a regular monthly fee. It took 1 year for me to sign up a megawatt of customers. They're all pretty much small business customers. We've got Safeway, Whole Foods, the Honolulu Museum of Art, the water park, sheet metal shops, auto body shops, and that's one person for 1 year. These storage systems have 10-year guarantees, 10-year life expectancies on them, and so when Don asked me to talk a little bit about kind of what's real, where is the technology today, I wanted to kind of bring a couple of specifics like that to the room so that it can help kind of inform the conversation of where does the distributed storage industry stand, and how quickly can it scale? And if you think about STEM and maybe our closest two competitors, if there were 3 companies in the market, we each had 3 salespeople, and we were out selling for 3 years, that'd be at that rate would be 27 megawatts of storage that distributed customer-sided storage we could have on the grid 3 years from now. So that's assuming no acceleration. So I just want to kind of put that in perspective. Next slide, please. What does the customer get? I mentioned the Honolulu Museum of Art. They're a unique customer in that they're right next to a threshold, so they're trying to stay below a threshold so that their tariff doesn't change to a higher demand charge tariff. And you're seeing on the upper right there a screenshot from a moment when they were 11 months into a 12-month effort to stay below a threshold and peaked above that 300. That little orange tip of that spike is the STEM battery system discharging them and keeping them below 300 at that 300. And you've got to stay below that for a year. For most customers, what we're doing is more, every month we're doing that kind of peak shaving, and we're creating just a demand charge benefit. You see the Honolulu Museum of Art system there in the bottom right or bottom left, and that's our modular system. We've got 56 of those towers out on Oahu now that make up the 1 megawatt project that I described. Each one of those towers is an 18 kilowatt 2-hour battery tower, modular tower. And then we show the customer their electricity usage, and we show them what the battery system is doing, and we try to empower them to make smart decisions. So you see the heat map there. We've got different software tools that kind of let them hone in on when are their peaks occurring, and maybe they can look for outliers. We can help them figure out why things are happening. I'm getting text messages on my phone a couple times a day right now because Watanabe Floral is having a really busy week, and they keep hitting these peaks because what's coming up on Sunday? Mother's Day, right. So one of their 2 busiest weeks of the year right now. And so, when I get these messages, hey, they just 91 kilowatts. So those tools are all part of this, and the customer gets that. We're really trying to help them take an active role in their energy, but the battery system is also there to deal with the spikes that maybe they weren't fast enough to control or didn't have time to because the shop is full of customers right now. Next slide, please. So what are we doing for the grid? And we've got a screenshot here of what the utility sees. And so this is a live tool that we presented to our project team at HECO last year. Right at the end of the year there, we went down and met with system operator folks. I'm really honored to have them in the room. I won't point them out because I know they like to stay under the radar, but those are our customers for this product in the long run. Right now, it's still kind of in the testing phase in the project team, the distribution planning group that we're in. But the dots on the screen there show the location of all the storage systems that we have on Oahu right now, and I think kind of the metrics across the bottom get to the really key fundamental principles. At some point, this needs to be automated and become more machine to machine. But you see sort of status availability. The status is we've got 1 megawatt of available energy, 1.65 megawatt hours or power, 1.65 megawatt hours of energy available that have been installed. I'm sorry. What's available right now is that bottom left number, so 0.6 megawatts is available. Why isn't that number exactly the same as what's installed? Well, the way that our business model is set up is the commercial customer comes first. If they're using their system for peak shaving, then it's not seen in the aggregation. It's not part of that 0.6 megawatts that's available. We also have restrictions against backfeeding. So if a customer's got a solar system, Watanabe is a great example that I mentioned, they're probably exporting or coming really close to exporting in the middle of the day, and so the storage system that's sitting at their site will not be seen as available in this aggregation because that would, using it would just cause further exports. So that available number is always less than what's total installed, and so we take the complexity out. We don't make the system operators think about, well, which system do I call on? In the future, we can also divide these up, though, into the 4 or 5 quadrants of the island. We could go all the way down to the individual circuit level, but at some point, you don't have enough systems for that to matter. Now you're back to sort of calling on an individual system. Next slide, please. our fidelity is increasing with this toolkit. And so, you know, just as a kind of a rule of thumb, I think it was Vinod Khosla, VC, said, you know, a lot of times people overestimate what technology can do, what improvements we can make in 1 to 2 year time frames, but we underestimate the change that will occur in 10 years. And so here's where we were a year ago. This is our dispatch tool that we showed to the, you know, to our project team last June. It was, if you would like to schedule this resource, you've got to pick the next 15-minute increment coming up. And so if it's and it has to be at least 15 minutes away. So if it was 2:10, you could start an event at 2:30, and you could pick the events in 15-minute increments up to 1 hour. Last month, we dialed that dexterity down to the 5-minute increment. So now if it's 2:04, you can schedule an event at 2:10, and you can schedule those increments, you know, in 5-minute increments. And by a year from now, hopefully less, we'll be doing 1-minute increments. So we're really trying to kind of, you know, move forward in lockstep. But this tool is currently available. This is an actual live resource. I would do a demonstration, but that's an actual resource on the grid that would actually deploy megawatt right now. Next slide. I think we're on the last one, or we may be at. Oh, last one here is that the real-time kind of feedback. This is also kind of where we're at, you know, where does rubber meet the road? Where are we right now today? We can show the utility, the site-by-site feedback, but we're not during the event, but we're not able to yet show them the fleet response feedback. However, we can see it in our own operations center, and we just haven't hardened it yet. So just to give you an idea of kind of where exactly does the technology stand, we've got the ability to see during that event that's been called a couple of minutes ago, how's it going, which system is providing what, and over the course of the event, the allocation may change from one system to another depending on how the event is going. We can see all that. We haven't fully packaged that into a hardened, you know, cyber secure display for the utility customer, but it's in the works. Our next step with this, last slide, is to take this to a more machine-to-machine operation in a project called Shines. We have got larger scale implementations using this same control platform across in CalISO. We're building out 85 megawatts under the same, from the same procurement that Jesse mentioned that AMS is part of, with Southern California Edison, 340 megawatt hours. Those are more like a demand response construct. It's a farther ahead notification. It's a little bit simpler. What we're doing here is really trying to tightly integrate with utility and show if you want a more immediate sense of status and availability and be able to control it, that's what we're building out with the Shines program that also includes Siemens and GE Alstom Grid. So I'll end it there and leave some time for questions. Thank you.
Very good. So we have 5 minutes for questions. Sorry about that. So questions for our panelists? Yes. Thank you.
As the infinite bus gets less infinite, you know, how are you dealing with protection issues, namely ground fault current changes due to less generation on the system, or will the DER systems be able to provide you the ground fault current, let's say a power plant for the infinite bus used to do? I ask this because, you know, as a utility owner, basically, for base, we are dealing with protection issues. And I'm just wondering how you guys might be dealing with protection issues for microgrids or bearing ground fault.
So this is where I show some of my geek side. Mike Evans here from S&C. The traditional grid has the fuses in. In fact, as you well know here, your fault levels are actually falling as you're taking rotating machines off. So you're going to need to change some of the types of lateral protection you have to make sure they're programmable so they can change in time. But you also have some new technology that you could deploy. So for example, those smart switches I showed actually have the ability to change protection curves in real time. So if they detect a fault, they can get greater discrimination and allow for that part of the grid to be protected. In terms of the power electronics, there's going to be a limit on the amount of per unit current you're going to get out of a power electronic device. So maybe 1.5 times. It's not going to be to the infinite bus range. There's also a side issue with this. As your fault levels go down, which means your impedance is going up, you're now going to have more and more voltage challenges. So as the grid changes to more and more of renewables, you're going to start to see voltage control be much more of an issue. And that's going to be proportional to the amount of renewables that come on the grid. So it's going to have some of we change. There are ways of dealing with that, but it's to show you some of the controls in the grid are going to have to change.
So one add to that, technology-wise, it exists. I think it's iteratively going to grow, improve from a responsiveness and a fidelity level. Challenge we see is the disruption and protection that's needed is not, it's being caused by non-participants in the model. I'll keep coming back to how is it paid for? We're seeing the bigger challenges, not that the technology isn't there, but how to make the investment relative to where the return is coming from and stack it up against all the other things the utility is having to deal with. Because right now, well, you've got somebody that will deploy solar, they'll put the inverter in, they're not looking to put any of the protection devices in. They're not interested in paying for it. None of, with respect to my colleagues that are pushing the distributed energy solutions into the industry, they're talking about the gen side, not the distribution protection side, and the market, if you will, the business model. Who's going to provide the protection and balancing to go along with the technologies that I think exist across.
Very good.
Yeah, so can I ask a follow-up to that from what Keith asked? So I want to ask if we can try to think about Keith's question and ask the panel if you have any thoughts about, rather than simply just responding to a drop in fault current and things like that Keith's inferring, as we think about grid modernization, are things that can be done as part of the grid modernization work to keep fault currents at levels that actually are more in line with what traditional devices or devices that are deployed today are still able to operate effectively. And I ask that from sort of as a leap from what Jay Griffin talked about this morning. At the end of the day, we all have to modernize a grid in a way that's most economically efficient. And I wonder if any of you have thought about the other approach. Is it easier and cheaper and faster to do things to the grid to address the fault current issue rather than to simply respond to it, or maybe a combination of both of them?
So I'll start, Colton. It's a combination of. I think the preventing of is standards-based. It's how this stuff comes on and how it's operated. I'll stop short of saying who should operate it, but somebody's got to provide that operating model to go along with it, and you're going to have to marry some reactive to when it goes outside the bounds of. There's technology. It's really right now, I would say, more of an issue of who is either responsible for or allowed to apply that technology to address the issues you're describing.
With the fault level reduction, there's also a frequency impact. So as you know, we just talked the fault levels from here. Now you're going to have a less stable grid from a frequency standpoint. So that really opens up a market for storage, how you can, it's well known, it's well documented. But there's going to be twofold issues to deal with from a technical standpoint. I think it's both. I don't think you're going to be able to replace the fault level because there's just so much to replace. It's going to be a combination. Anticipating the changes, which your planners can do, and start to enforce the grid so we can actually add those in there. But then also think about the role for other services that DERs can play to actually increase that.
Very good. One more question, Colton, or?
No, not for me.
All right.
Any more?
Another question? Yes, front row.
Henry Curtis. You were mentioning that flickers will go up due to the current PV situation, but my understanding is this utility doesn't track flickers. So how would you suggest handling that?
So first off, I'm not saying that PV is causing flickers. I'm saying that as you have more PVs in, those systems will react to flickers in the grid. So you're going to have some clear cut out before they come back in. How you actually, you're right, and in fact this is not just a challenge here in Hawaii, this is a mainland challenge as well, that our industry fundamentally doesn't look at momentary outages. And I believe that the industry has to start measuring it. Where there's been customer feedback, where they're unhappy with the grid, real stories, smart metering in 2012 in Florida was able to show that the customer experience from the grid was much worse than what was being measured from the utility side. And that was called momentaries. And there's a recognition of that, and they created a KPI for that called Customer Experience Index. But that impact was able to change the approach to distribution automation to start eliminating those flickers. But you have to start measuring it to begin with. But in fairness to HECO and all the island utilities, this is a whole utility issue. And I think momentaries are only just starting to really bubble up to the surface as being part of the pain point. But frankly, you have to start measuring it.
Anyone else? We have reached the end of our time. I do want to, if you can help me thank our panelists. And if you do have questions, please, they will be here. You can come ask. So we have time for a 15-minute break, and we'll get back together.